Okay, so let's go over the last two types of Riemann sums that we're going to go over in this class, which are midpoint and trapezoidal. So, how do we do this? Starting with our left one, this is where we're going to use our midpoint one. And midpoint, I'm assuming you've already watched the first video, so I'm going to move a little quicker. Oh, this is my second time recording this, so I'm going to move a little faster because I messed up on the first time. Instead of doing our rectangles from the left or the right, now we're just going to do our rectangles from the middle point. So, and I'm going to do even subintervals for both of these, and then I'll do some example problems in my next video that do non-even subintervals. But let's say we want to go from 0 to 4. Let's talk about that. So our x distance is 4. And I want to do 4, I want to do even subintervals. So how do we get even subintervals? Well, let's say we want to do 4 even subintervals. So I want to do 4 rectangles. If I say subintervals, that's the same as rectangles or trapezoids if we get to trapezoids, when we get to trapezoids, but we're going to do 4 rectangles. So 4 subintervals / rectangles. Another fancy word you may see is partitions, especially when you get to college. The word they're going to use is partitions. That also means the same thing. I'm not going to write that though because I don't think I'm going to use that in this class. So then our delta x equals our x distance divided by number of rectangles. That's 4 divided by 4, which is just 1. So our delta x is 1, so now I'm going to draw the base of our rectangles. I'm not going to draw the heights. But every time I move 1 on the x-axis, I'm drawing these little dashed lines. So I'm moving 1, I draw dashed lines, move 1, draw dashed lines, move 1, draw dashed lines, boom. Okay, and lots of things mathematicians name are named for their simplicity. So midpoint formula, I'm literally looking at the midpoint of my rectangle. So I'm looking at the middle between 0 and 1, that's 0.5. And that is going to be the top of my rectangle. The middle between 1 and 2, that's 1.5. That's going to be the top of my rectangle. From 2 to 3, 2.5, top of my rectangle. And finally, from 3 to 4, 3.5, that's the top of my rectangle. Okay, and I want to get through this one kind of quickly, so the only thing I'm going to really point out is if we look, I'm going to highlight yellow areas are where our rectangle is over approximating. And then blue areas are where our rectangle is under approximating. It'll show up in a second. And at the end of this, we'll talk about if we're over approximating or under approximating. But we can see that just by sort of looking at it, this approximation, like we have an almost even amount of yellow and blue. So our approximation is pretty good here. Because all this area here that we over-approximated, well, we also under-approximated some of this area. All this area that we over-approximated, we under-approximated, and so on. Okay. And now we are trying to approximate the area under the curve. We're not finding the area under the curve, we're approximating it. So we are approximately doing the integral from 0 to 4 of our function. We're approximately doing this. And the reason we're approximating is because we're only using 4 subintervals instead of infinite subintervals. So I'm not taking a limit yet. And we're adding 4 rectangles. So we're going from 1 to 4. We're adding 4 things. This is our top bound. And we're doing our midpoint. So how do I get my midpoint? Well, this is going to be, and our f of I, sorry, I'm going to need to see that part down there. This part here, that was my little notes. Well, when I is 1, we want 0.5. When I is 2, we want 1.5. When I is 3, we want 2.5. So it already updated, but what we're going to do is we're going to take I and we're going to subtract 0.5 from it. And then that's still going to be times delta x. Which in this case, our delta x is still just 1. And now let's go ahead and write out what this integral is going to be equal to. Well, it's going to be equal to I'll do it this one. F of 0.5 times 1 plus f of 1.5 times 1 plus f of 2.5 times 1 plus f of 3.5 times 1. And that's going to give us all of our rectangles, and I'll actually even denote this is like rectangle 1, or the area of rectangle 1, the area of rectangle 2, area of rectangle 3, the area of rectangle 4. And you can go ahead and pause the video here and try and figure out what that area is yourself, because I'm not going to show the steps in between how I get this. Because I can just look at the graph and figure it out, or if you want to, you can use your actual function and plug it in, but I'll let you do that on your own, and when I come back, I'll have what our final area is going to be. Okay, coming back, I got that the area was 11, if we're looking at all these points. So our area of our 4 rectangles is 11. And now let's talk about our over approximation or under approximation. Well, just as a reminder, this is our midpoint sum. Midpoint Riemann sum. And our approximation is pretty good. It's not perfect, but the other piece to this is, if you look at the graph I gave you today, I didn't give you a strictly increasing or decreasing graph. What I gave you is a concave down graph. And for midpoint Riemann sums, our approximations or if we're under approximating or over approximating, it has to do with the concavity of our function. Our function is concave down. And it's hard to tell based on this graph, but these blue areas are actually a little bit bigger than these yellow areas. So we're actually under approximating. So we have an underestimate when concave down, and the other part to that is an overestimate when concave up. So this is an under approximation, an underestimate. All right, on to our last type of Riemann sum. Here, this function is, what is this function again? This function is, if I remember correctly, and I might check myself, f of x equals the square root of x minus 1. Yeah, that makes sense. Okay. So this is our function here, and our last type of Riemann sum, I had to choose a different graph because I want this to be a good picture. This is a trapezoidal sum, a trapezoidal Riemann sum. So what we're going to do is, instead of using rectangles, we're actually going to use trapezoids. And we're going to do, let's start with our delta x to figure out where we're going to draw these trapezoids. But our delta x, I want to go from 1 to 5. So what is our distance there? Well, our distance is 4. So our x distance is 4. And I'm going to still use even subintervals for this, even number of rectangles. So if we want to do an even number of subintervals, well, let's do 4 rectangles then, since our x distance is 4. Or I'm actually telling you, I want to do 4 subintervals, so we're using 4 rectangles. So 4, not rectangles, trapezoids. Although one of our trapezoids is going to look funny. So this means our delta x equals 1. 4 divided by 4 is 1. Okay, now we can go and we can draw our sort of trapezoids. And I'm just going to start by doing my delta x part. And I'll do it in green. So I'm starting at 1 and I'm going to 2. Then I'm going from 2 to 3. 3 to 4. And 4 to 5. And this gives us 1, 2, 3, 4. 4 trapezoids that we're going to make. And our first trapezoid, well, this is the other part of our trapezoid. It's at 0, so this trapezoid is actually going to end up being a triangle, which I went on a very deep scavenger hunt to try to decide if triangles are trapezoids. Triangles are not trapezoids, but we're going to pretend this is a trapezoid. We're going to pretend this is trapezoid, and this length here is going to be 0. Like this trapezoid here, when we get to here, which I'll do next, it has a length on this side and a length on this side. This length is going to be some number. This length is some number. This trapezoid on this side has a length of 0. So now here, I draw my next trapezoid. And I'm just going to go ahead and draw all the trapezoids. And we end up with these trapezoids here. And we can tell automatically what's happening if it's an underestimate or an overestimate. Well, we can look and we can see this is clearly an underestimate. We're missing pieces of our okay, clearly this is an underestimate, and I'm realizing now that I made a mistake on my the other thing that I said, and I really don't want to re-record this again. So we're just gonna go back and I'm just gonna fix it. I mixed these two up. It is an underestimate when we're concave up and an overestimate when we're concave down. Because the reason I realize this is because our midpoint Riemann sum is a similar error analysis to our trapezoidal sum. So, sorry, apologies for that. It's an underestimate when we're concave up and an overestimate when we're concave down. Because if we look here, this function is concave up, and it's an underestimate, and that should be the same as our midpoint sum. Okay, moving on. Now let's actually start calculating the area of this. Well, what is the area of a trapezoid? The area of a trapezoid is equal to 1/2 of a plus b times our h. And let's just go, and I'm going to label on our actual trapezoid, not our triangle, because that'll be a little more clear what's happening. But one of our sides is A, the other side is B, and our H, so this is our A, this is our B, and our H is actually our delta x. So let's rewrite this in terms of what is actually happening. So we're going to have 1/2 A plus B. Well, A is going to be our function value at a specific point. That's going to be one of our lengths. So let's say f of xa plus f of xb times delta x. So this will be our xa, the left side will be our xa, the right side will be our xb. Okay. And now we're just going to go through and we're going to actually figure out all the areas. I'm just going to add all this up. This is going to be the sum from 1 to, we're doing four trapezoids. You just stop doing rectangles. 1 to 4. And our xa here, we have f of 1 plus f of 2. Or it's actually, I'll just write it officially out. And really, I should use better notation if I'm using summation formula. So let's rewrite this. We'll do it as f of x sub I plus f of x sub or actually, let's do it this way. F of x sub I minus 1 plus f of x sub I times delta x. So why did I do it like that? I'll explain why I wrote it like that. Because this means that our I corresponds exactly to what I want. So if my I is 1, 1 minus 1 is 0, so I get f of x sub 0, well that's going to be f of 0. If I is 1, then, oh shoot. Okay, this is what I want. F of x sub I, because our I is 1, we're starting at 1, and 1 plus 1, or I plus 1. So I want 1, I want 2, and then when I is 2, I want 2 and 3. When I is 3, I want 3 and 4, and then 4 and 5. Okay. So now I'm just going to write it all out. This is going to be our approximation of the area under the curve. We have 1/2 times f of 1 plus f of 2 times 1 plus 1/2 f of 2 plus f of 3 times 1. And each of these is going to be a different trapezoid. And our final one, f of 4 plus f of 5. That's what. Okay, I'm going to zoom out a little bit because this one looks a little long. Okay, and again, you can go ahead and pause the video. I'm not going to do this math out. You can figure it out by yourself. And when I come back, I'll have what the actual area is. Okay, and coming back, I did use a calculator for this, by the way. We should get that the area is approximately, or the area is 5.146. And I already said this, but I'm going to say it again. When we're doing our error analysis, our trapezoidal Riemann sum is the same as our midpoint. So it should be an underestimate when concave up. And an overestimate when concave down. And if you want to talk about which one's a better approximation, the midpoint is a better approximation than the trapezoidal, but this isn't an error analysis class. Although lots of practical math, when you get to the higher thing, does turn into error analysis. It's a whole field of study. But this goes over our last two Riemann sums. Thank you for watching.